I'm Tom Scherer. I'm an extension agricultural engineer with North Dakota State University. And today we're going to be looking at the pumping plants that supply water for irrigation systems. In the northern plains and in lots of the parts of the United States, center pivots are the predominant method of irrigation. It allows us to irrigate rolling hilly land, droughty soils. They're very popular, they're low labor, but they are pressurized sprinkler systems and they require a pump, obviously in the water source. The pump is the main user of energy, and it's a large user of energy. People that own irrigation systems, that may be one of the largest energy consumption devices on their entire farm. The only way you can really tell if they are operating efficiently is to do a pumping plant efficiency test, which is really quite simple. What we're doing is testing, we're going to measure the energy going in to the pumping plant, and we're going to measure the different parameters and calculate what the energy is actually going into the water in terms of power. So this is an electric system right here. You can see it's a large pump, and there's a shaft that goes down. This is called a deep well turbine pump. There's a shaft that goes down, connects here. The pump is down in the well, and it lifts the water up. As you can see, it goes off over here, goes up to the pivot point, and then from there it goes out in the pivot. These are a large asynchronous universal motor. They're very efficient. Typically, these larger three-phase motors like this can be anywhere from 88 to well over 92, 93% efficient. They're very good pumping, but there is some inefficiencies, and over time you can get wear on the impellers, you can get wear, and that can cause inefficiencies. And so we're going to do a pump efficiency test on this system to find out how it's performing against what we consider a very good operating system. And the first thing I want to do, which is really find out where the static water table is before the system is running. This pump hasn't been running for a couple of weeks, so the water level in the well is probably going to be down around 15 to 20 feet below the surface. This well is, at this particular site, is about 90 feet deep. We're standing on top of an aquifer here, and that is the depth to the aquifer. So you can, if you subtract 20 feet from 90, there's about 70 feet of water here to supply this pivot. So I'm going to go ahead and, before it ever starts, I'm going to try to measure determine where the static water table is, just so I know I have a reference point. So when we measure the water level, when this pump is actually pumping, I have some kind of an idea of what the drawdown is in the well. This thing has markings on it of how many feet it's going down. This is an old system, and over the years we've lost a few feet. Luckily I haven't, but some of my predecessors got these caught in the pumps and lost. So we're now at, we start at 162. So as it is, I'm sliding this down through this. This pipe goes down and connects into the casing that goes down into the well. From the weight on it, I can feel that it's going down. It's not hitting anything. So we are now down, it's 178. There you go. Okay, as you can see, I hit the water level there. Static water level is about where I expected. It says it's at 177. And if I pull this up, I can see here it says 163, and it's about a foot to here, so 162. So we have almost exactly 15 feet to the water table right here. This is a common sight here on most irrigation systems. You have a standard propeller type meter, but here in the northern plains, after a few years, these have a propeller inside in the pipe, and the freeze-thaw cycle seems to wear out the bearings, and quite often they don't work. So for a pump test, I need an accurate measurement of the flow rate so that I can get an idea of how much actual power is in the water. So we're going to use an ultrasonic flow meter, and I'm going to clamp on the pipe right down here. So I have a nice long, as straight a stretch of pipe as I can get, so I have uniform flow, and then I'll get a more accurate reading. The heart of an ultrasonic flow meter that we use is called a transit time flow meter, and it's these crystals. And we put a couplant on them, That's what this material is. It's just to make sure that they make good contact with the metal surface. As you can see, this one's fairly rusted. The way they work, it's really a very simple procedure. We have a microprocessor-based ultrasonic controller there, and I'm going to hook it up to these crystals. The water is going to be flowing this way. They'll send a pulse and they'll bounce off this side. That's why I put this at an angle, so that I got clean pipe on the inside. Not some of the stuff down here might be rusted. It bounces the signal off to there and bounces up, picks it up here, and then it reverses it and it shoots a signal this way. So one signal is going with the water, the other is going against it. It measures the time difference between the two, and then based on the time difference, and we know it's water, it then can calculate what the average velocity of water is in the pipe. And if I know the inside diameter of the pipe, which I can get from measuring it, then I can calculate, the processor here will calculate the flow rate for us and give us a good accurate estimate of what the flow rate actually is going out through this pivot when we turn it on. You can put different types of transducers on these. So I'm just programming this to tell it what type of, what the setup here is. And there it'll calculate how far apart those transducers are. It's saying we got about 625 gallons a minute. And the end gun is not on. Is that correct? Nope. If the end gun were on, it would probably be drawing more, but we don't want to test that anyway. Now that the pump is running, we measure the flow rate. I need to know what the pumping water level is, because the pump is lifting it from that depth up to this point, and then my pressure gauge is telling me what the pressure is, so between that I can get what the total head is, and then if I multiply that times the flow rate, I can estimate how much actual power is in the water. And then when we get our electrical reading, then we can compare the two and determine what the efficiency of this pumping plant is. It says 186, and we started at 162, so that means we've got 24 feet of pumping water level. So at 600 gallons a minute, this has only dropped 6 feet, which is a very good well. Or from 15, I should say, that's 9 feet, so you're getting quite a bit of water for a small amount of drawdown. To get the energy in, most new digital electric meters can actually be programmed by your local rural electric to actually read out what the actual power in kilowatt draw is at all the time. This one's not programmed that way, but I'm pretty certain most of them can program it so that it'll tell you what the current draw, what the power draw is. And once you have the power, this is the input. You got those other measurements. You can calculate what's in the water. You can do your own pretty much estimation. Actually, the existing meter on this system appears to be, at least it's turning. You can see the counter going around. So what we're going to do is time it to see how long it takes to pump 1,000 gallons. Should be about 1.5 minutes at 600 and some gallons a minute. When the 8 there gets even with the zeros, I'm going to start it and then time it when it shows 0.8. Because every time it rolls over is 100 gallons, which is not unusual on a totalizer. If I calculate the flow rate using this meter, it said I pumped 1,000 gallons in 1 minute and 45 seconds, and 45 seconds is 3/4 of a minute. So if I divide 1,000 by 1.75, that comes out to about 570 gallons a minute. Now we just measured with our ultrasonic, and it shows that this pump is actually putting out 625. So this meter is reading low, which is not unusual. It probably indicates the bearings are getting wore and it's just not turning as smoothly as when it was new. So this would not be a reliable guide for estimating the flow rate from this pump. Well, now that we've completed the pump efficiency test, we can always, a farmer can always do their own. Really all he needs is a good working and accurate flow meter and a good accurate pressure gauge. Now this one is relatively new. This reads pretty good. When we compared it against our readings, they were identical. This is an older flow meter, but if the flow meter has been fixed up or is new, you get an accurate flow meter. So once you got the flow, once you got the pressure, then the most difficult part sometimes is figuring out how far are you lifting the water from in the well. In this case, we know we were able to get in and measure it pretty easily down to 24 feet. That sometimes is the most difficult because there's many wells that can read, some pump from 70, 80 feet down, and it's not always easy to measure that distance. So hopefully from information about when the well was drilled, you get an idea of what the pumping water level is. And once you have that, then you can calculate how much actual power is in the water. Well, in order to do the pumping plant efficiency calculations, we need to measure the energy out, which is in the water, and the energy in, which is through the electric meter. And to measure the water horsepower, we need to know the flow rate and the total head. And this simple formula shows how to calculate that. And the total head is the pressure at the pump, which we measure with a good pressure gauge, the depth to the pumping water level, and then we have an estimate of the friction loss in the riser pipe, which is usually a small value. And once we have that, we can calculate the water horsepower. And so looking at the calculations for the test we just did, the measured flow rate was 625 gallons a minute. The pressure in the pump was 41 pounds per square inch, or 95 feet a head if you convert it to a head of water. And the depth of the pumping water level in the well that we measured was 24 feet. And we estimate the friction loss in the riser pipe is about 4 feet. So if you add those up, the total head is 123 feet. And we multiply that times 625 and divide it by the constant 3960, and we see that the water horsepower is 19.4 water horsepower. So that's the energy out. And then we measured the energy in by reading the electric meter, and the energy in was 25.2 kilowatts. So when we divide 19.4 water horsepower by 25.2 kilowatts, we end up with 0.77 water horsepower per kilowatt hour. And then we compare that against what we would expect from a very efficient electric irrigation pumping plant, and that which will produce about 0.885 water horsepower per kilowatt. So if I take our 0.77 divided by 0.885, I get 87%. And that's compared to a very efficient electric irrigation pumping plant. And this isn't something that has to be done every month. It only has to be done once a year or once every other year. But it's a worthwhile way to check how well your pump is pumping water, how efficiently it's using power. The motor sounds very good. It was very quiet. Some were noisy. If there's any bearings going out, we didn't hear any of that. But I did some quick calculations, and this one's running at about around 80 to 85% of standard. Now, there might be some reason. It's an old pump. There might be wear on the impellers. The impellers may not be adjusted properly. There's a number of reasons. It's certainly not due to the well, but the pump is probably, because of age, it probably needs some work. Now, whether it's economically feasible to do that, it's probably not, because it's quite expensive to pull. But it does tell you where you're at, and if we were to do it in a couple of years and it was getting any worse, then it might be worth investing to fix the pump and bring it back up to near 100% efficiency.